Okay, hello everyone. Uh, I think for today's class, I think I just finished off. I think the power series finished until the finding the radius of convergence and interval of convergence. So basically, to get the radius of convergence, we take the ratio test, and then we check the interval to get the interval of convergence. Okay. I will give you later the maybe just put the exercise on the notes and upload the notes after the class. Okay. So I would like to continue. So after the power series, the next part will be how to represent a series as a function. Okay. So here will be okay. Suppose that we have this functions 1 over 1 minus x, and as we mentioned, I think in the geometric series we can mark the geometric sum as a 1 over 1 minus x as long as the ratio is less than 1. Okay, the absolute ratio is less than 1. So we could see that the 1 over 1 minus x we could write as a series x with power of n starting from n equals 0. So this is one simple example that we can somehow write down the power series as a function. Okay. And from this part, we're going to get a lot of conversion for many functions that has the same forms. Okay. For example, if we have like 1 over 1 plus x squared, we could imagine that in forms of 1 minus x squared, and then we could change the x with x squared, and many more that we can do with a similar form. Okay. So let me write here. So we say that the series is a power series function 1 over okay, let's say we have the interval -1 to 1, that's the ratio, right? And we can also write the 1 over 1 minus x as sum, or we can take the limit for the partial sum of the Sn of x, like we did in previous pages, where the Sn x is 1 plus x squared plus dot dot dot. So this is the partial sum. Or nth partial sum. And normally, as the n increase, then Sn becomes or approximate better for functions or two functions for -1 to 1. Okay, and then we can see on this part here. Let me put here. If you see the picture, this is the red curve. The red curve is 1 over 1 minus x. So basically, what we are observing is that the partial sum, we start from 1 plus x. So let's start with 1 plus x, which is the linear equation. It's perhaps somewhere here. It's 1 plus x, maybe like that. And then we have 1 plus x squared, which is the quadratic function, this one. And then we increase, it becomes cube, s3, maybe here. And then s4, another quadratic part. And then s5, okay, like that. Now what we can observe is the interval on this -1 to 1. Now if you see any differences here, we are going to ignore that, okay, because that is not in our observation in observation here. Right? So we are going to focus here, and we are going to see that when we increase the s2, 3, 4, 5, and then 8, 11, and then somehow if we increase more and more, it's getting close to this red line. Okay? So this is going to be true when we have the interval -1 to 1. Okay. So we can say that the power series, okay, that represent these functions 1 over 1 minus x, it can also be expressed to represent any power series with many functions with similar forms. Okay, with similar forms. So perhaps if we express, maybe right here, if we express 1 over 1 plus x squared, right, like this, we can express as 1. Okay. Now our goal, or our reference is 1 over 1 minus x, which is, this is the sum of this. So our idea here is we are going to exchange this -x squared as in x with the x power n. Okay? So we can write here, this is going to be okay. Or if you want to make it clean as a series, we can write okay. And if we would like to know the interval, that is basically the ratio, right? So we could say that it should have, or that means converge on -1 to 1. Okay. And similarly, if we have 1 over 2 plus x, so our goal is to make it into 1 minus x. But now we have 2, so we can factorize 2. So we can factorize 2. So this become 1 plus x over 2. Okay. And then 2, 1 minus x over 2. And then this will be half, okay? And this will be the x to the power of n, and we can exchange with negative x over 2. Basically, that is, basically we change all the functions into 1 over 1 minus x. And then we can write, if we want to combine all together, we can do that because it's the same 2, right? We have 2. So we can also write this as and then for the convergence, we can see that we have negative x over 2 for the ratio. So that should be less than 1. Or this is, we could say that this could be done by this. So converge on negative 2 to 2. Okay, one more example for this one. Let's say we have x cubed over x plus 2, or 2 plus x. Notice that we can separate this, it becomes x with power of 3 multiply 1 over 2 plus x, which we have done before, right? 1 over 2 plus x. So this will be x cubed, and then I will just rewrite the previous example, right? So just rewrite all. And basically done. But if we would like to make it more clean, we can combine. And we can also write an alternative form if we would like to know, like if we want to remove the plus 3 to make it more clean, so we can make it start from 3 instead. So we can write this as n start from 3, and then exchange the, and since it's 3, so I will take it early, so I will minus 3 for the xn, and then this will be also minus 3, which is minus 2. But for negative 1, we only have at least 2 choices, n or n minus 1. And for this one, this will be n minus 1. Okay. But again, to make these substitutions or exchange in the forms, I would like to suggest you to check again the regular forms, whether they are still similar or not. But if you would like just to end up until the previous part here, that's still okay. No problem at all. Okay, any questions first? I think logically, what we do here is basically take reference on the geometric series 1 over 1 minus x, and we are going to represent that in terms of series. So if we have many forms of functions that we can manipulate, if we can manipulate the functions and make it into the 1 over 1 minus x, that means we can make them into series, or into power series to be precise. Okay. Okay, so let me take another page. Let me add. So the second theorem for the power series is basically related to derivative and integration. So the series can be derived for all the terms and integrate for all the terms, okay, for all terms. So this is, we call the term by term differentiation and integration. So basically, if we have a power series, it has the positive radius convergence, and defined by that series as Cn x minus a with power of n, and it is differentiable, and because it's differentiable, it should be continuous on the interval of a minus r, a plus r. We can write derivative forms, and then write also the integrations. Okay. And all the radius of convergence should be the same. And we can also write this in the forms of ddx basically we can derive directly the series, or we can derive one by one and then make conclusions. I think it's too big. Let me write more smaller. Okay, now if we could see a functions, and then we know that it can be derived or integrated from our known forms. For example, our best reference for this topic will be the 1 over 1 minus x. Still, this is our best chances. And if we differentiate this, then we get 1 over 1 minus x and then squared, right? And then simply we can also differentiate the terms. 1 plus 2x plus 3x squared plus da da da. And simply this is okay, so basically we can derive each term or we can derive the series itself. Okay. So this becomes a new function. So we can represent the new function 1 over 1 minus x with power of 2. And by the way, we can also replace the n by n plus 1 if you want to make the n start from 0, which is, I think, very basic forms. And this could be n plus 1, and then this will be x power n. It will be the same. Okay. Just changing n with n plus 1. And then the radius of convergence will be the same. It will be 1. Now the next example, suppose that we have ln 1 plus x. Okay. Now we would like to know what is the series representation of the ln. So we would like to write in terms of series. Okay. Now so far, we can replace 1 over 1 minus x with, so we can replace x with other terms. We can differentiate or we can integrate. Now, the idea is, we have the ln. Where is the ln coming from? Okay. So where is this coming from? Derivative, integrations of what? 1 over. Right? Yeah. So we can start with 1 over 1 plus x, right? So we could see that the ln is basically the result of the integrations, right? Okay. So basically, remember that the 1 over 1 plus x is going to be 1 minus x plus x squared minus x cubed and so on. Let me write here because I think it will be confusing. So this will be, I will write again the previous page. right? Okay, so basically, we can integrate all the terms. So 1 minus x so x and then and for sure at the very end there should be a constant, right? So by looking at the terms, we could try to guess and check the series. And starting positive, so we have n minus 1 for the starter. And since we start from n equal 1, then this will be over n, right? 1, 1, 2, 2, 3, 3, 4, 4, right? And plus c. For the ratio or x is less than 1. Remember that this will be ln 1 plus x, right? We can actually consider the constant. If we put x equals 0, this will be 0. This will be ln 1, which is 0. So constant 0. Agree? Right. So we can erase the constant. So we can check the constant by taking the x equals 0. So at x equals 0, ln, let me just write ln 1 like that. It's become 0 plus constant. So constant also 0. So finally, the ln 1 plus x is sum okay. Okay, one more example on this, and then finish the subtopics. Okay, then the next will be the last in chapter 11, and maybe after that, maybe next Tuesday we are going to have overview, and maybe exercise, and I will discuss the what kind of midterm which we have. Okay, one more example. Let me write here, example. The next example is if we have a function, tangent inverse x. So again, this is also related to our reference. Okay? So for this subtopic, our reference is going to be the 1 over 1 minus x, or we should get into this kind of structure. But the tangent inverse x, the structure that we might get is 1 over 1 plus x squared, right? So that's our clue. So we are going to take that 1 over 1 plus x squared, make this reference, and then make it into the tangent, which is going to be the integral, right? So if we take the derivative, this will be 1 over 1 plus x squared, right? So the tangent inverse x is basically the integral of 1, which is going to be integrations from 1 minus x squared plus x4. Okay. So let me write x minus x cubed over 3 plus x5 over 5 minus x7 over 7 dot 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 plus constant. And again, this is tangent inverse x. We could argue that at x equals 0, this will be 0, this will be 0 plus c, so constant is 0, right? So the tangent inverse x is x minus which we can write the summation. Okay, so since it started positive, then I think we can start from n, but it's 0, so it's 1, right? And then you see that the denominator is the odd value, the odd number, 1, 3, 5, 7, and so on. So this will be 2n plus 1. And the numerator will be the power with the odd value also, right? So we can just write x to n plus 1. And to make sure that is correct, we can check like 0, which is going to be consistent throughout the terms, which is going to be correct. Okay? Okay, the next part will be the final subtopics in chapter 11, which is the Taylor and Maclaurin series. Okay. It's interesting because the idea is somewhat unique, and it will be, I think, quite helpful, at least for approximations in some models and engineering formulations. Okay, I think we can start. So Taylor series, I will write first the power series that we have done before, which is just a regular f of x, and then we have the center at a. So we say that x minus a is less than r, which is the radius of the convergences. So to make it the coefficients, okay, if the so if we put, if x is equal a, then we could have all the terms with a inside will be equal to 0, right? Because it's x minus a. So if x equal a, then it will all be 0. So the f of a will be just a coefficient, the first coefficient, and then the other part will be 0. Okay. Now, the important thing in the Taylor series is the Taylor series is a combination of the power series and its relations of the functions with its derivatives. Okay. So suppose that this is f of x. Okay. So we are going to derive this f of x. And let's say we have the f, let me write this derivative, ddx. So we write f prime x. Okay. The first coefficient will be gone because it's a constant. The second term, it is linear and then becomes a constant. So C1. So let me write maybe here. C1 plus. Now we have C2. So this will be 2C2 x minus a. And it's become linear. And then plus 3C3 x minus a squared plus 4C4 x minus a cubed, and so on and so forth, with the same radius convergence r. And then the same if we take x equal a, then the f prime a will be C1. Okay. Now do the same operations. I think I will do until we get the third derivatives. So this will be gone, the C1 will be gone. So we have 2C2 and then plus. Now 2 is coming to the front, right? 2 multiplied by 3. But I would not multiply becoming 6. So I would just write 2 multiplied 3 C3. Okay? And then we have plus 3 multiplied 4 C4. Okay? And plus the same radius of convergences. And the same idea, if we take the x equal a, then the whole terms will be 0. Okay. Now the last part, suppose that we are going to have a good pattern or a unique pattern. So we take the third derivative. Okay, the constant will be 0. And then this will be 2 multiplied by 3 C3 plus, now it's become 2 multiplied by 3 multiplied by 4 C4 x minus a becomes linear. And suppose that we have coefficient 5. We are going to know that this C5 will have a coefficient in front of the terms. We are going to have 3, 4, 5. This will be x minus a and then square. And then this will be x minus a. Okay. And then the same idea, taking x equal a. Then the third derivative of a will be 2 multiplied by 3 C3. Now looking at the terms that we get from the f of x and then f prime, f double prime, f triple prime, see the coefficient in the front. It is 2, 3, 4. Okay. Now we have 2, 3, 3, 4, 3, 4, and then 4, 5, and so on and so forth. This also has this similar pattern, 2, 3, 2, 3, 4, 3, 4, 5, okay, and so on and so forth. Then we could argue that these terms could make another series. So, and this could be written as just a 3 factorial, right? C3. Okay. And if we could see all the f prime, f double prime, f triple prime, whenever we take that, suppose that we have n for the how many we derive of A, this will resulting in 2, 3, 4, 5, until some n of Cn, which we can simplify. This becomes n factorial of Cn. And by looking at the coefficient, we can rewrite in terms of Cn that this will be equal to notice that this n is not a power, it's derivative. Okay. And even for n equals 0, this is still valid because the 0 factorial is 1, right? Okay. And now, to make it into series, the Cn, since it has this forms, that it will change along with the derivative, the second, the third, fourth derivative. We can put this into our power series. Remember, the power series has the Cn x minus a. We can replace this Cn with this, and that's how we define Taylor series. So maybe one by one. Let me start from this one first that we get. Okay. So start from the power series. Okay. Start from the power series, and then the idea is the power series. We take the derivative several times. So derive. We get some idea on how the coefficient looks like, and this coefficient we can input here. And this becomes another series. Okay. This becomes another series, which we call the series as a Taylor series. So basically, Taylor and Maclaurin is based on a combination of terms that is going to be expressed from the function and its derivative. And you will see that the first term, perhaps it will be maybe the first derivative, the second derivative, or if you would like to start from 0, so you just have the 0, the first coefficient, and then the second coefficient would be the first derivative, second derivative, and so on. Okay. So this will be the series that defined by the Cn here. So we take this into here and change the Cn in the power series, and then take from 0 this f of a, f prime a, 1 factorial, f double prime a, 2 factorial, and this will be the same. This is all the n will be the same for each term. So this is 0, so only the function. This will be n equal 1. So first derivative, 1 factorial, and this is linear functions, right? And this will be the second derivative, 2 factorial, quadratic functions. This is the same, and 4, 5, and so on. Okay. So you could begin to write most of the regular functions in terms of the Taylor series, like sine, cosine, and some other like tangent inverse as well. So this is more generalized formulation. So before we had the so-called the 1 over 1 minus x to begin with, but now we have a more generalized formula. Okay. Now it works for most of the basic function in Taylor series. At least 8 functions, at least. Okay. Now, if A is equal 0, so if A is equal 0, we get another terms, which we call with another name. This is the Maclaurin. Okay. So this is the Maclaurin. So the difference is only for in the terms of the center. And since the Maclaurin doesn't incorporate any A, it much more makes sense to take the Maclaurin in a more general use. But it doesn't have to be A, because A is Do you have any class after this? Huh? Do you want to finish early for my class? Maybe just add just a 20 to 30 minutes. Is that okay? Okay. So I will just continue and then finish 25 minutes. Okay. Just a bit more. Okay, now we have the Taylor and the Maclaurin. Okay. So we can start, take some example. Okay, taking some example. Perhaps starting first is maybe the f of x 1 over 1 minus x. This is the one that we have before, but we can write this in terms of the Maclaurin. Okay. So taking this, taking x equals 0, and then taking the first derivative, and then take another derivative, and this will be 1 and 2, right? Or you can just write 2. And the third derivative we get, this will be 4, and then 3 will be coming to the front, so 1, 2, 3. So this will be 1, 2, 3, like that. And we can write from here, we can write the formulation for the f. This will be n factorial over 1 minus x and plus 1. And for x equals 0, this will be just n factorial, right? Basically. So then the coefficient is just n factorial over n factorial, which is 1. So then the final result, as we know, and this is confirmed by the Maclaurin series, this will be the coefficient. And since the coefficient will be equal to 1, so this will be just equal, since this is equal 1. Okay? Okay. Now another functions that is going to be represented quite a lot in the Maclaurin series is the exponent, okay, the exponent, the e to the x. Okay, so if we get the f of x e to the x, imagine that e to the x, if you derive, it will be the same for all the functions, right? So we can just write that since it's going to be the same, the f with derivative first, second, or nth derivative, this will be also the same e to the x. So the x equals 0 will be just 1, right? So the Maclaurin series will be equal to f so this, since this is going to be 1, so we can just write x with power of n over n factorial. Or if we want to expand, this is going to be 1 plus x over 1 factorial plus x squared over 2 factorial plus da, da, da. And if you want to check the radius of convergence, let me write here, let me write that. If you want to check the r, we can take the ratio test. an plus 1 over an. Okay, so this is x, and if n factorial, we can cancel the n plus 1 factorial, and it's becoming n plus 1. Okay, so we have squared the x over n plus 1, and since this is going to be 0, right? This is going to be 0 for every x, so we can write this is going to be 0, so we can write by ratio test series converges for all x, so r will be, we can write infinity for all x. Okay, so it's applied for all x. Okay, but there is another question. if from here we know that the e to the x is the sum of this, right? But the question is, how can we determine? Have a power series. Power series representation. Now the best way to get into the answer is by the approximation. So the best way is, so if we take, let me write here. Okay, so remember the Taylor start from here. So we can start from the partial sums that will limit for each term we increase the n. Okay, so when we increase the n, we can limit the terms. So let's say we start from partial sums Tn. We name the Tn. So Tn of x. And let me distinguish this from the original Taylor with another variable for the terms. Let's take I. So now why we need the partial sum? Because in partial sums, we can define the limit of the terms. And continue until plus fn of a over n factorial x minus a with power of n. So we can end the series on the n, right? Because of the partial sums, and we can see that for functions e to the x. Let's say we take the e to the x because the term in the e to the x we can approach easily from the graph. Okay? We can see that from the e to the x we can get the t1x basically from here. So t1x means that we have here 1 plus x, t2 this 3, 4, 5, right? So t1x for the e to the x is 1 plus x, and then we increase 1 plus x squared over 2 factorial, and then we can also take t3 of x, 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and let me just add one more. So we have polynomial, at least polynomial easily to visualize if in the graph. Okay. So if we take this into the graph, maybe you can take the GeoGebra as well. Then you will see that our graph, let's say here, by looking at this side here, this is our starting point, 1 plus x, our observation. We start from here, and I think similar with the previous example that you mentioned, that if we increase the partial sum, the n in partial sum. So T1 that we increase become polynomial the squared, the quadratic function, and then we increase become a cubic, and then we can increase again, become 4, 5, and you will see that as we increase the n, the line will going to take closer to the e. Okay, it's going to be closer and closer. So as n getting larger, it's getting close to our e to the x. Okay. So we can write here. That's actually our f of x. We can write in terms of limit. And if we there are some spaces in between the t and our f. Let it be the space, a gap, that we name as, usually we name as error or the r or remainder. Then we can write the remainder is the differences between the functions and the partial sums. Or we can write the f as the partial sums plus the r and the remainder. This is called the remainder. Okay, so the next part here is there are at least two theorems that is correlate with this definition. So then so the question is, if we can show that the limit for the r approaching 0, then our approximation will be true. Okay. So our goal is to prove the limit of the Rn of x will be 0. Okay. So let me just give you the theorem first. And let me give you the theorem. So this is going to be our approximation, the Tn plus Rn for our f. Tn is the Taylor polynomial for our partial sum of f. And then if the limit for the remainder is 0, if this limit 0, then and for the radius convergence x minus a less than r radius is convergent, then the f will be equal to the sum of its Taylor. So f will be equal to this t. And then to get the remainder, to get the limit of the remainder equals 0, we need this, and we need this, which we call it Taylor's inequality. So Taylor's inequality is actually some numerical method or approximations to approximate our unknown functions. And suppose if we cannot approach using regular method in math, we could always approach in numerically or by approximation. So it says that this fn plus 1 of x, this is terms from the Taylor, right? Suppose that this is going to have some m, value of m, for this interval. Okay, for this interval, we say the distance, and then we could define the r. It should be less equal. Basically, this is the terminology from the Taylor series. So which means that the r is always less equal of this m over the n plus 1 factorial. N plus 1 factorial is the terms from our original Taylor. This is also from our original Taylor. For x minus a less equal b. Okay. And we are going to use this as a reference to get the r. So basically, what this inequality do is basically we change the terms of the f above here. We change with some value m. M could be understood as the least or the highest possible maximum value that can be achieved on some interval. For example, if it is maybe if it is trigonometry maybe 1, okay, or if this is another another number as well that is going to be that it can be compare with our art. It could be written within this inequality. Okay. So m can be any number. It can be any number. Okay. So how to use this? So I think this will be the last part. Okay. Okay, so first we prove this. Okay, so first we prove. Let me take this into the new copy here. Okay, so for n equal 1, and then assume that the second derivative, let's say the second derivative, because it's n plus 1, so let's start from n equal 1 so that we can assume the second derivative is, let's say this is going to be equal to m or less m. And in particular, we can write that this will be less than m. So the distance or the interval will be from a to a plus d. Okay. So the integrations of the f double prime t dt should be less than the m dt. Okay, starting from a to x and then a to x. Okay. So if we integrate the f double prime, it will result the f prime, right? It will result the f prime. So we can write the f prime x minus f prime a is less equal, and m is just a constant, just a regular value. So we can write m, and then this will be m x minus a. Or we can write the f prime x less equal f prime a plus m x minus a. Now let's let's integrate once more. So we could get the f, okay, from the f prime. So if we take integrations with respect to dt, okay, so we are going to get f x minus f of a. This is the same from a to x, from a to x. So this is like a parametric. So less equal f prime a, and then x minus a. And then this will be m let me change this x into t to avoid confusions, to make the integrations complete. So m, we integrate t minus a, it's become t minus a squared over 2, and then exchange t with x. Okay, I think now it's correct. And now we can write the f of x minus f of a minus f prime a x minus a less equal m over 2 x minus a squared. Okay. And this is the first equations. Okay. Now let's see the second equation that we would like to compare. We take the R1. Okay, we take the R1x, which is, this is going to be f of x minus t1. Remember, t1 is 1 plus x, okay, for this argument. So we will try to compare. Okay. This will be f of x minus f of a minus f prime a x minus a, right? Only the t1. Okay. So the R1x should be less. It should be less equal than, since we have here that this is equal to this, and since the R1 is equal with this, which is the T1 is this, then the R1 should be less equal than this. Okay. At least that is the R1 that is the highest possible component that can be achieved through the R1. Okay. So R1 should be less equal than the m over 2 x minus a squared. Or if you want to write in a more convenient way, we take the absolute value to get only the value itself. So this is going to be just to prove that our inequality that is we built from the beginning, this will be true if we look at this R1. We can do the same comparison. If we take maybe third derivative or fourth derivative, and we take maybe R2 and R3, this will have the same component that we have from the f. From the f, maybe f double prime or triple prime. So this is just to show that the Taylor's inequality. Let me write here. This proves Taylor's inequality where n is equal 1. So this is an assumption. Okay, at the beginning, we start from n equal 1, so that we assume that our calculations, we assume that we have the second derivative, that suppose that it is going to be m. And when we rearrange the structure, we are going to get the same idea for the r and all the t, okay, all the t and f. So we could also, if you want to rearrange, like for example, n equal 2, then it will be the third derivative. If n equal 3, this will be going to be the fourth derivative, and you will see the same components. For example, our components here is taken in the form of this part. Okay, this is our component. Our component for f of x minus f of a, which is basically, this is the same as our r, which we define as f of x minus t1. If we would like to take another n, maybe n equal 2, then we could say that this will be R2, and this will be f of x minus t minus x minus t2x. Okay. So we could have another arrangement and then another set of formulation here that maybe it has more components, but it will be equal to the remainder. So this is just to prove that the Taylor's inequality, we can explore the approximations. Okay, there is another example on the inequality, but I think I will keep that next Tuesday. And I would just like to let you know just another example. This is the sine x and all the partial sum for its Taylor. So our goal within this one here, which I think I will take this into next Tuesday, I will just write this. This will be the Maclaurin for f of x equal sine x. Okay. And then lastly, this is at least some basic functions that will be included in our subtopics. So we have 1/1 minus x, which we already discussed previously, e to the x, sine, cosine, tangent inverse, and ln. I will try my best to get into all these components and how to get it. Basically the same thing. We take the f, take the derivative, maybe 2 or 3 or 4 derivatives. For Maclaurin series, take x equals 0, and that will be the coefficient. And then we put into the component, remember the Cn, our Cn now is f n of a over n factorial, or in Maclaurin it will be a equals 0. So we put all in that coefficient, and we put in the pattern, and then we conclude the series. That's how we go. So actually, it depends on you. If you want to maybe to add some memory in your memorization, which I want you to not just memorize it, but you know how, because in the end, at every problem and question in exercise, you need to confirm, right, whether your answer is correct or not. So you need to know how to get this. So the idea from the functions, you have some set of derivatives, get the coefficient, and put back into the series. Okay. So that's how you get it. And for example, there is some interesting point in sine and cosine, which you can see from this two series. Sine and cosine, basically they are complementary. Or we can say that sine, if you want to derive sine, it becomes cosine. You will see that x derived become 1, x cubed derived become x squared, but the 2 factors will be cancelled with the 3. Okay, so this is also the same, 5. Go down, become 4, and then 5 here, cancel with the another factorial, which is going to be 4 factorial. Okay, we could also do that as well. So series can be derived, can be integrated, so you could play with that as well. Okay. So I think, as I mentioned, I will be finished up to here. We're going to see again next Tuesday. When will be the holiday part? I forget the dates. What date now? It's 28th. Maybe